systems of the body require energy to perform their biological work. All the body systems require energy, including, of course, the muscular system. The basic source of the energy generated in the body is a substance found within the cells called adenosine triphosphate, or ATP. When energy is required, the ATP is broken down, liberating large amounts of energy. Within the muscles, prior to exercise, small amounts of ATP are present in the myofibrils. When a stimulus to contract is received, the ATP breaks down, activating the sliding filaments. This produces muscular contraction and thus movement of the body. However, there's only sufficient ATP present in the muscle to power one explosive contraction, and a system of rapid replenishment of ATP is essential. This replenishment is achieved in the following way. The breakdown of ATP is a reversible reaction. This allows the products of the reaction, adenosine diphosphate, or ADP, and phosphate, to recombine or resynthesize to form ATP again. There are a number of different sources of replenishment for the ATP. These are known as energy pathways. Sporting performance depends on the efficiency of these different energy pathways, and therefore this is a very important area of study. Some sports require only a single explosive movement. The energy for this single movement comes solely from the breakdown or splitting of the ATP already stored in the muscles. If we plot a graph of the duration of maximum effort against the percentage use of the various pathways, we see that these very short duration explosive activities rely totally on ATP splitting. Repeated muscular contractions require the immediate replenishment of the ATP supply. This is achieved by the rapid breakdown of another energy-rich phosphagen compound also present in the muscle, creatine phosphate, or CP. The splitting of each CP molecule provides sufficient energy to resynthesize one molecule of ATP. The ATP can now produce one more contraction, but then it must be resynthesized again by further CP splitting. There's sufficient CP stored in the muscle to sustain all-out activity for 8 or 9 seconds, after which replenishment from this source falls off rapidly. In the longer sprint events, such as the 400 meters and the 100 meters freestyle, another source of stored energy is called upon when the supply of CP has been exhausted. Sugar or glycogen, stored within the muscle, breaks down to produce the energy for the resynthesis of ATP. This process is called glycolysis, and because it occurs initially in the absence of oxygen, it's referred to as anaerobic glycolysis. This process also produces large quantities of lactic acid as a byproduct. When the lactic acid in the muscle reaches a high concentration, the muscle becomes fatigued and performance falls off. The onset of muscle fatigue due to the build-up of lactic acid occurs after about 60 seconds of intense activity, although the athlete's tolerance to this fatigue can be greatly improved by training. The energy pathways outlined previously, ATP splitting, CP splitting, and anaerobic glycolysis, are valuable sources of energy for sprints or periods of intense activity in team games. But because they rely on stored energy, they quickly become exhausted. If energy is required for a longer duration, a much more sustainable energy pathway is needed. The aerobic metabolism fulfills this requirement by using energy stored in body fat together with oxygen from the air, hence the term aerobic metabolism. In a complex series of chemical reactions, very large quantities of energy are made available for the resynthesis of ATP. Glycogen continues to be an essential ingredient in this process. The byproducts of the aerobic metabolism are water and carbon dioxide, which are easily disposed of and do not detract from the athlete's performance. These are the energy pathways used by the athlete. ATP and CP splitting for explosive movements and short sprints, anaerobic glycolysis for longer sprints, and predominantly the aerobic metabolism for endurance events. Many sports, including team games and the endurance events, use a mix of energy pathways. In these, longer periods of moderate activity are powered aerobically. Short bursts of intense activity are powered by the short-term pathways. The energy pathways should not be thought of as separate mechanisms that switch on and off one at a time. They're interrelated and overlapping, each contributing to the replenishment of ATP when required. This concept is known as the energy continuum. It's very important for the athlete to analyze the energy requirements of his or her particular sport. A training program can then be designed to increase the performance of the specific pathway or pathways being used. The food we eat is, of course, the basic source of energy for the work our bodies perform. Food is digested and stored in various forms throughout the body for use by the appropriate energy pathways when required. This diagram shows the relative amounts of the energy stores in the body. ATP, 1 kilojoule, CP, 4 kilojoules, glucose and glycogen, 2,500 kilojoules, fats, 80,000 kilojoules, and protein, which is not normally used as an energy source, 30,000 kilojoules. The very small amounts of stored ATP and CP demonstrate the need for rapid replenishment. The ATP is replenished by the energy released from the relatively small glycogen stores and the much larger fat stores. Since the glycogen stores power the anaerobic energy pathways and are a major contributor to the aerobic pathway, it's essential that these stores are maintained at a high level. We do this by eating a sufficient amount of carbohydrate in the diet. This diagram shows the energy intake requirements of a typical athlete. The importance of carbohydrates in the diet can be clearly seen. Major sources of carbohydrates are cereals, bread, pasta, fruit, and vegetables. Carbohydrate is converted to glucose, which is circulated in the blood and stored in the muscles and liver in the form of glycogen. These stores are then readily available for the replenishment of ATP via the anaerobic and aerobic pathways. Excess carbohydrate intake is converted to stored fat, which can then contribute to aerobic energy production. In sports requiring endurance, the athlete can increase glycogen storage by increasing carbohydrate intake in the days preceding the event. This type of diet is known as carbohydrate loading and should be planned in conjunction with the coach.
What time does the race start tomorrow, Will?
10 o'clock, I think. So that means we'll have to leave home about 9 o'clock. Is that okay, Joe?
Yeah, that should be right.
I mean, an early breakfast. You have to have breakfast before 7 o'clock.
A small, high-carbohydrate pre-game meal, 2 to 3 hours before the event, is also often recommended. There are ample stores of fat throughout the body, and these are easily maintained by a balanced diet. Fat intake is converted to free fatty acids, which circulate in the blood and are stored as triglycerides in muscle and fat tissue. These stores are then available for aerobic energy production. Meat, cheese, margarine, nuts and peanut butter are sources of fat in the diet. Protein from lean meat, cheese, eggs, fish, poultry, cereals, vegetables and milk builds the cells and tissues of the body. In extreme circumstances, for example towards the end of a marathon, some of the protein in these tissues break down to supplement other exhausted energy supplies. Vitamins and minerals are needed for the many complex biochemical processes involved in energy production, as well as many other body functions. In most cases, a balanced diet will supply sufficient vitamins and minerals, and supplements are unnecessary. One exception, however, is in the case of female athletes, who may need iron supplements due to loss of blood during menstruation. Such a course of iron supplements should only be taken on the advice of a doctor. Water is also vital to our bodies and our performance. Water accounts for 60% of our body weight and makes up about 80% of our blood. The athlete must drink a lot of water, particularly to avoid heat injury through dehydration when exercising in hot and humid conditions. The quantity of food that we need to eat is proportional to the amount of energy that we burn up during exercise. While training regularly, an athlete may need up to twice the food intake of a person who does not exercise. However, during breaks from training, the energy requirement falls, and the athlete must eat less to avoid putting on weight, which is usually in the form of excess fat. Careful maintenance of correct body weight throughout the season ensures that the correct balance has been maintained between food intake, energy stored, and energy used. As we've seen, the nutrients in the diet provide energy stores throughout the body. These stores require ample supplies of oxygen from the atmosphere in order to produce energy via the aerobic pathway. When we start to exercise, our energy requirement rises and is met by increasing our oxygen consumption or oxygen uptake. Oxygen uptake is abbreviated to VO2. Immediately after the start of exercise, there's a time lag before the energy requirements can be met aerobically. During this period, a large portion of the energy requirement has to be met from the more immediately available anaerobic sources. This is referred to as oxygen deficit. When exercise stops, oxygen uptake falls rapidly to begin with and gradually returns to normal. This allows replenishment of the various energy stores and provides energy for the elevated respiration and heart rates until they return to the resting state. Low levels of exercise, for example walking, require only a small increase in oxygen uptake. As the work intensity increases, the level of oxygen uptake increases. However, a level is finally reached above which oxygen uptake will not continue to rise in response to further increases in workload. This maximum level of oxygen uptake is known as VO2 max. The VO2 max of an average Australian teenager is about 2 to 2.5 litres of oxygen per minute, and that of a trained athlete is in the order of 3 to 4 litres per minute. To take into account differences in body sizes, VO2 is usually expressed in millilitres of oxygen per kilo of body weight per minute. Thus, for the average teenager, this value would be 35 to 45 millilitres per kilo per minute, and for the trained athlete, 55 to 60 millilitres per kilo per minute. The varying levels of work intensity can be expressed as a percentage of VO2 max. For example, a light workload may represent 25% of VO2 max, and a moderate one 50% of VO2 max. The importance of oxygen uptake in total energy production is clearly shown on the graph. However, it also shows that energy requirements which exceed our aerobic capacity, or VO2 max, can only be met anaerobically. Note that also below the level of VO2 max, there's a significant contribution of anaerobic energy. Activity cannot be sustained for long periods at these high levels, mainly due to the build-up of lactic acid and the exhaustion of anaerobic energy stores. The level at which the increase in lactic acid in the blood prevents long-duration sustained aerobic activity is called the anaerobic threshold, or the onset of blood lactate accumulation. Training programs are therefore designed to raise the level at which the anaerobic threshold occurs, as well as improving maximal oxygen uptake. The higher the anaerobic threshold, the higher the percentage of VO2 max that can be sustained for long periods, and therefore the higher the potential aerobic performance. The higher VO2 max level achieved by training enables the athlete to use a lower percentage of VO2 max to meet aerobic demands. If, for example, two runners having VO2 max values of 60 mils per kilogram per minute and 50 mils per kilogram per minute were asked to run at a pace of 6 minutes per kilometre, both runners would consume about 35 mils of oxygen per minute for each kilo of body weight. Because of the difference in their aerobic capacity, the demands placed on their cardiovascular and muscular systems would be markedly different. Runner A would be working at 58% of VO2 max, whereas runner B would use 70% of VO2 max. Runner A, therefore, could sustain the pace for a longer period and feel less distressed than runner B. We've seen the importance of oxygen uptake in aerobic performance. Now let's look more closely at the mechanisms of oxygen uptake. Oxygen is taken into the lungs and is transported by the bloodstream to the working muscles, where it's extracted and used by the muscle cells. The more oxygen that can be supplied to and then used by the muscles, the greater the aerobic performance. Oxygen uptake can be represented by this equation. The important factors affecting oxygen uptake, VO2, are the volume of blood pumped by the heart, cardiac output, and the volume of oxygen extracted from the blood and utilized by the muscle cells. We'll look at these factors in more detail. Firstly, cardiac output. Cardiac output is measured in litres of blood pumped by the heart per minute and is calculated by multiplying the stroke volume, that is the volume of blood pumped by each heartbeat, and heart rate, that's the number of heartbeats per minute. Note the relationship between cardiac output, stroke volume, and heart rate. As stroke volume and heart rate increase in response to exercise, they produce a corresponding increase in cardiac output. The volumes involved in cardiac output are illustrated here using quantities of milk. A trained athlete during maximal exercise may have a stroke volume of 120 millilitres and a heart rate of 200 beats per minute. This results in a remarkable figure for the cardiac output, 24 litres per minute. The second critical factor in oxygen uptake is the volume of oxygen extracted from the bloodstream and utilized by the muscles. This can be measured by finding the difference in oxygen content between the blood in the arteries flowing to the muscles and in the veins leading from the muscles. This is called the arterial venous oxygen difference. So the equation for oxygen uptake can now be written as VO2 equals stroke volume times heart rate times the arterial venous oxygen difference. Most of these factors increase during exercise and are further improved by training. Sporting activity involves vigorous exercise, and the responses of the body, particularly energy replenishment, must be rapid and effective. These responses begin even before the start of the event. Both the heart rate and the respiratory rate increase in anticipation of the imminent replenishment needs. Energy for the start and for initial acceleration is provided anaerobically. However, oxygen uptake immediately begins to rise rapidly, increasing the aerobic contributions to energy supply. This increased oxygen uptake is achieved by the combined effect of the following mechanisms. The respiratory rate rises, increasing the volume of air ventilated by the lungs by as much as 15 times. These large volumes of air ventilated by the lungs are sufficient to supply all the oxygen that can be carried by the bloodstream and utilized by the muscles. The stroke volume increases, the heart rate increases, and the arterial venous oxygen difference increases. Referring to our equation for oxygen uptake, we can compare the figures for an untrained person at rest and during maximal exercise. As can be seen, the major increases in stroke volume, heart rate, and arterial venous oxygen difference combine to produce a 1300% increase in VO2 or oxygen uptake. This graph of oxygen uptake against cardiac output illustrates the relative contributions of stroke volume, which increases initially and then levels off, and heart rate, which increases in a linear fashion until it reaches its maximum figure. Two other responses to exercise are important: the redistribution of blood flow and a rise in blood temperature. During exercise, up to 85% of the total blood supply is redirected to the working muscles so as to maximize oxygen availability. This redistribution of blood is aided by a proper warm-up. After the workout, a warm down is equally important in order to redistribute the blood back to the other essential organs of the body. The temperature of the body rises during exercise. This is because about 75% of the energy released in the breakdown of ATP is in the form of heat. The rise in temperature aids performance by improving muscle metabolism and nerve transmission. But if care isn't taken, it can lead to heat injury during long periods of intense activity. Correct training improves the performance of the body systems. This is achieved by the adaptation of these systems to meet the increasing demands placed on them. Training should concentrate on the specific components of fitness required for the particular sport. For example, explosive and sprint events require improved anaerobic capacity, and endurance events require improved aerobic capacity. This diagram illustrates the changes that follow anaerobic training. ATP and CP stores increase, glycogen stores increase, the amounts of the enzymes which are involved in anaerobic energy production increase, the amounts of lactic acid present in the muscle during intense exercise increase, showing that more anaerobic energy can be produced and that the athlete's tolerance to lactic acid has improved, and the size of the fast-twitch muscle fibers increase. This enlargement of the muscle fibers, which visibly increases the girth of the muscle, is known as muscle hypertrophy. Aerobic training produces these results. The ability to store glycogen improves, as does the ability to both store and use fat in the aerobic metabolism. Improvements in both transportation and utilization of oxygen result in increased oxygen uptake. And finally, hypertrophy occurs in the slow-twitch muscle fibers. Looking in detail at the improvement to VO2, we can see that training results in increases in stroke volume and, to a lesser extent, in the arterial-venous oxygen difference, all of which combine to improve VO2 by 15 to 20%. At submaximal workloads, the required cardiac output is achieved by the increased stroke volume and a correspondingly reduced heart rate. This lowering of the heart rate is an easily observed measure of an athlete's aerobic fitness. A graph of heart rate against workload, before and after training, illustrates the lowered heart rate during submaximal exercise and at rest. Note also that the maximum heart rate does not change with training. By these and many other changes, including skill and motivation levels, training improves performance. Every workout, whether in training or in competition, must be preceded by a correct and adequate warm-up and be followed by a correct and adequate warm-down. The routine of warm-up, workout and warm-down allows the body to adjust physiologically from rest to intense exercise and back to rest again, effectively and safely. There are 3 stages to the warm-up: gross motor activity, flexibility exercises specific to the sport and practicing the specific movements of the sport. Gross motor activity involves low-level exercising of the large muscle groups involved in the particular sport. This literally warms up the muscles. The rise in temperature increases the speed of the biochemical energy-producing reactions, increases the rate of muscle contraction, and reduces the viscous resistance within the muscles. This allows full and free movement and lessens the danger of injury. The blood flow is redistributed into the working muscles, including those of the heart. Exercising at this level stimulates the respiratory and cardiovascular systems, thereby increasing oxygen uptake. Next, specific flexibility exercises should be performed. This ensures joint mobility and fully stretches the muscles prior to the workout. This in turn reduces the chance of a torn muscle or tendon or other injury occurring during the workout. Lastly, the specific movements of the sport should be practiced. This refreshes motor skills and finally prepares the specific muscle groups to be used in the activity. Care should be taken to maintain muscle temperature right up to the start. Otherwise, much of the value of the warm-up will be lost. The warm-down assists the body systems to recover gradually and safely to their resting levels. Lactic acid concentrations are dispersed and metabolized, and energy stores are replenished. A particularly important aspect of the warm-down is the redistribution of the blood flow out of the muscles back to the other vital organs of the body. This is achieved by the pumping action of the muscles themselves during low-level gross motor activity. Flexibility exercises should be included in the warm-down. This restretches the muscles that have been contracting during the workout. The warm-down can also be a very effective time for improving flexibility levels. There are two main purposes of physiological testing. Firstly, it provides accurate measurements of the individual athlete's fitness levels, and secondly, it allows the athlete and the coach to monitor progress and improvements achieved during training. These are members of the Australian Institute of Sport Diving Squad. They're undergoing physiological testing at the University of Queensland.
4.30.
This is part of their first testing session at the university, and the results will provide a baseline for monitoring their physiological development during their time with the squad. These tests include the skin fold thickness test, which is a measure of body fat and body composition.
6.5.
This is the Wingate test of aerobic power, using a bicycle ergometer. And here, the diver is being tested for muscle fatigue on a Cybex dynamometer.
Keep pushing it out. 5, 6, let's go. Let's go. 8, let's go. Going well. That's right. Control. You can do it. Keep going. Pull back on.
While the elite athlete often has access to sophisticated facilities and equipment, there are many simple tests that provide very useful information. Tests like these can be carried out at school or club level and then used in the accurate planning and monitoring of the individual's training program.